Okay, so in this lecture we are going to finish our study of quantum teleportation that we continued in that we started in the previous lecture. So I'll draw the circuit diagram once again. And I have this is state 0. This is a continuation of the previous lecture. Now there are these measurement operators and the classical bits coming out of it, A and B. And as we discussed in the previous lecture, this was Bob's end. So this wire belongs to Bob, and so that's the deal. What's happening is Alice and Bob start with a 1 E bit of shared entanglement, and this is the unknown quantum state which Alice has. This wire also belongs to Alice, and this wire is Bob. Alice applies a gate between its qubit, which was a shared entangle between Alice and Bob, and the qubit. It applies the Hadamard gate, and then it makes two measurements. Depending upon the outcomes of the measurement A and B, it sends these classical bits to Bob's end, and Bob, depending upon that, Bob is going to apply the gate X and Z. If A and B are both 0, nothing happens. This wire goes straight through. If A and B both are 1, Bob is applying X and Z, and we'll see that the state V shows up at Bob's end. So this was the state V, and Bob recovers the state V over here. So this is teleportation accomplished, and mind you, so this is the circuit diagram for quantum teleportation. Also, mind you, this is the quantum teleportation for an unknown quantum state. Alice and Bob need not know what quantum state is there, and still they are able to accomplish this task. So let's look at it. What exactly is happening in this circuit diagram? So So let's say you had that was my unknown state V. I had control not gate, and that helped me prepare. I won't normalize the state, just to let you know. This is 0011, a shared state between Alice and Bob. The state here was 0 plus 1 on just this one wire. And then we apply a control not gate here. And these are the measurements. So ultimately, the joint state here for the 3 qubits is alpha given by a tensor product V, this state, and the Bell state. So one can show that this state actually has hidden 4 Bell states inside it. So by Bell states, I mean the same terminology which we use for superdense coding. Let me write down these 4 states again. These 4 states. Uh, well, I would encourage you to try this yourself, but alpha can be written as that's how I can write down alpha. So I just try to clean this up and write it on the top of it. So that's the idea. I can write alpha in terms of a linear combination of all the four Bell states. So what you can do is that take V as any arbitrary state and try to see that this indeed is true. So V is this, and this guy is going to be tensored with the Bell state, and I can, when I expand V in terms of its basis, T0 plus S1, Ket1, I can write down alpha, the state, as a linear combination over the four Bell states, the four orthogonal Bell states, and at Bob's end, I can express the state in terms of V, and X naught get applied to V, which essentially, well, V is nothing but T plus S1, T0 plus S1, so on and so forth. So now it's rather easy, right? Like now, essentially, the idea is the following. What really happens is that Alice can distinguish all these four states. So these four states, the linear combination, the first two qubits over the top are with Alice, and only the qubit I highlighted as red, this guy was with Bob. Okay. So Alice can distinguish either of psi 00, psi 01, psi 10, psi 11, and then send two bits of classical information out of this measurement. So essentially, here is what Alice is doing, trying to distinguish the two orthogonal states, Alice's measurement. And Alice can send two bits of classical information A and B to Bob, and depending upon what those A and B are, Bob applies these two gates and finally gets the teleported state. So I'll again draw the circuit over here. Yeah. So finally, as you can make out from this circuit, if Alice gets psi 01, then Bob applies an X operator to the state to recover back the state V. I'm using V and psi interchangeably, it doesn't really matter. So this is the circuit where Alice and Bob again start with an entangled pair, and then Alice measures her half of the two qubits into one of those orthogonal states, psi 00, psi 01, psi 10, psi 11, and depending upon the outcome, sends two classical bits of information to Bob, where Bob receives it, and depending upon A and B, Bob applies the following gates to recover psi back. So try this calculation, expand it in fully in terms of the bracket algebra and try to form it out. But that's essentially the idea of quantum teleportation. So rather simple circuit, but something very profound. As we said that, look, this is in principle infinite amount of information, because to send T and S to infinite precision, we need infinite amount of information to express them decimally. So you're sending this amount of information uh, to Bob, and the beauty is that in this entire protocol, in the gates we applied, nowhere we required psi to be known by ILS or Bob. So in some sense, if you look at deeply, this suggests that quantum teleportation might have some cryptographic advantage to it. Also because none of the parties knows psi, and yet psi ends up at Bob's state. And again, as far as the resource inequality is concerned, it is exactly the reverse of superdense coding. Alice and Bob had one shared entangled pair, plus two classical bits of information communicated, A and B, and this was able to accomplish 1 qubit of quantum communication. So again, this greater do sign just means accomplishes. So this is a resource inequality. These such inequalities are called as resource inequalities. So one question, interesting question might arise is that does quantum teleportation imply faster than light communication? Think about it. This is a circuit diagram. Does it imply, see, these gates and measurements are happening instantaneously, but essentially Alice still needs to communicate these two qubits A and B to Bob, and that cannot happen faster than light. So no, Alice and quantum teleportation, just because two classical bits of information still needs to be sent, and that cannot happen faster than light. So quantum teleportation does not apply faster than light communication. It just implies that an unknown quantum state can be sent across a quantum channel once you have a shared bit of entanglement and you allow uh, two classical bits of information to be sent. Thank you.